Alrighty. So I'm gonna go over this quiz. I forgot my Chromebook at home, so hopefully I'll be able to do it where you can see it here. Alrighty, so on my first one, I had two half reactions. They're both at this point reduction half reactions. So when I looked up this value, it was negative 0.137 volts. And this was negative 2.92 volts. So we keep the one that is the most positive. So that would be this one. So that one just stays as it is. And then my other one is going to flip. So this one would become BAS, gives me Ba2 plus, aqueous plus 2 electrons. And I would take my 292 and I would make it positive because I flipped it. All right, so that is number 2. I'm supposed to do the standard cell potential. So negative 0.137 plus 2.92 is going to give me 2.78 volts. All right, number 1, I was supposed to write the overall ionic equation. So this one is going to be good to go because they both have the same number of electrons. So I don't have to do that. It already cancels out. So my overall net is going to be Ba solid plus my 10 ion. So the ion is always going to be AQ, and you've got to put your states on this net ionic. And then over here, 10 is my solid plus my barium AQ. So when I looked at these two half reactions, this one and then this one, the only thing I needed to cancel out was my electrons. And then my last one says, write the half reaction that is occurring at the cathode. And for cathode, it's red cat. So the reduction is happening at the cathode, and ox at the anode, that's my oxidation. So since this is my reduction, I'm going to write my reduction half reaction, being sure to include my states when appropriate. And that would cover that one. All right, on my next one, pretty similar situation. So I'm going to look up these values, 1.065 volts and negative 2.713 volts. So this one is going to stay as my reduction, and this one I'm going to flip. So it would become Na solid, gives me my Na plus my electron, and then that value would become positive. So for number 2, I'm going to put 1.065 volts plus my 2.713 volts is going to give me 3.778 volts. Good, very strong positive. That would make a good battery. It's positive and it's a pretty high positive number. You've got to show this little step to get points. That's why at the top I put show any kind of work, even if it's little easy ones, because you have to do that on the AP test. All right, overall, now to write that, this only has 1 electron, so I'm going to multiply everything by 2. So 2 Na gives me 2 Na plus 2 electrons. So now I'm through with these two, and here my electrons can cancel out, which is what I needed to do. If that would have been my N, then that would have been 2. So I'm going to write that out, Br2, and that's a liquid, plus 2 sodium solid is going to give me 2 Br minus AQ plus 2 Na plus AQ. And then my last one, once again, the half reaction at the cathode. So that's going to be my reduction one, the one that I did not flip. And remember, if you're writing the half reaction, that does include the electrons. So only the overall, but it does not when you're trying to cancel them out. All righty, let's see what we got going on at this one. What is the voltage produced by a voltaic cell consisting of a lead cathode in contact with Pb2+, and then an iron cathode with my Fe2+. So I have a couple of reactions going on here. I have my, these are what I'm going to get off the chart. Fe2+ plus 2 electrons goes to Fe, and then my Pb2+ plus 2 electrons goes to Pb. And those values are negative 0.440 volts, and over here, negative 0.125 volts. So once again, we're going to take our most positive one, which would be this one, and it's going to stay as it is. So that's going to be my reduction half reaction. Pb, that should be a solid. I should have put AQ here, and that value stays as negative 0.125 volts. And then I'm going to flip this one. Fe solid becomes Fe2+ plus 2 electrons, and that one I'm going to take my value and flip it so that becomes positive 0.440. All right, and then what am I supposed to do? So I'm going to find my E0 value. Is going to be negative 0.125 plus 0.440, and that's going to give me 315 volts. So that's my overall. Which is the anode and which is the cathode? So once again, red cat reduction happens at the cathode. So that means my cathode is going to be Pb, because remember the cathodes are made, or the nodes are made out of some type of metal. And my anode, and oxidation occurs, that's going to be my iron. And then it asks whether it was a good battery, and you could just put something as simple as, yes, it's a good battery because you have a positive E0 value. And if you have a positive E0 value, then it's going to make a good battery. All right, move down to the next one. So we have Fe3+, Fe. And then over here we have MnO4, Mn2+. So we have a couple of reactions going. I'm going to do my Fe3+ plus 3 electrons going to Fe. That's off of the chart, and it has a value of negative 0.04 volts. And then I need my one here, and that is, let's see what we got. All right, sorry, I couldn't read my own writing. So for my other one, it was a much more involved reaction, but once again, it was just straight off this whole half reaction. Let me get this out of the way, sorry. This whole half reaction was on your sheet. So I had MnO4 minus plus 8H plus 5 electrons gave me Mn2 plus 4H2O. So that is a reaction that already had to be balanced because remember this had some oxygen, so that's why the water had to be added, and then eventually that made the hydrogen added and continued on. And this value was 1.51 volts. All right, so that was definitely more positive. So this is the one I'm going to flip. It's going to become Fe, gives me Fe3 plus 3 electrons, and that's going to become now a positive 0.04 volts. All right, all of that's supposed to be calculate the E naught, kind of took up a lot of room, but now to get my E naught of the cell, I just need to add those two together. So 1.51 volts plus 0.04 volts is going to give me 1.55 volts. All right, so that's my answer to that question. All right, so now we need to write the overall net ionic. I'm through with this one. So if I look at my electrons, I have 5 in one and 3 in the other. This. Let's see if I can do this. So that means the common number is going to be 15. So I'm going to have to get 15 electrons on each side. So that means I need to multiply this one by 3 and this one by 5. So I end up with 3MnO4 plus 24H plus 15 electrons gives me 3Mn2 plus 12H2O. And then I'm going to do the same thing here. 3Fe is going to give me 3Fe. Whoops, never mind. Now let's change that to 5. 5 times 1 is 5. 5 Fe3 plus 15 electrons. And that's all I got down there. All right, so I did all of that so I could get these electrons canceled out. And that was the only thing that could cancel out. So now I'm going to put it back together for my net ionic. And I'm going to double check that I'm not dropping things. So I have 3MnO4 is an ion, so it's going to be AQ plus 24H plus AQ. And then here I have 5Fe, and that is solid. And so then we're going to go to our product side. I have 3Mn2 plus, that's going to be AQ, plus my 12H2O, which would be my liquid. And what else do I have down here? I have 5Fe3 plus, and since it's an ion, it's going to be AQ. So that is going to be my overall. And you notice when I did my overall, I added all those states back in. If you check it, you should be equal on both sides in regard to the elements and also in regard to the charge. So this would be what I got here. It would be 3MnO4 plus 24H plus 5Fes gives me 3Mn2 plus AQ plus 12 water plus another 5Fe3 plus AQ. All right, now we need to write the cell notation. So you put them in alphabetical order. So you're going to do anode and then cathode. So my anode is where my oxidation is happening. So that's my iron. So I write what makes up the anode first, iron. Then I do one line, what ion is going to be in solution. And then I do 2 lines to separate it from the cathode. Cathode, it starts with ions. Remember, it's called an ion sandwich. So Mn2 plus, and you also would have MnO4 in that solution. And then this was a little tricky part. Some people put this. I was kind of lenient on it, but anyway, some people put this. That cannot be a node. It needs to be a metal. So you could have put platinum, which is inert, or that's probably the most realistic choice. Some people put Mn, which is a metal, and I also let that go. All right, and then predict whether E cell is larger or smaller when when Mn2 plus. So remember, we're looking at standard is 1 molar. So if I go to 0.25 molar, that's going to increase that concentration. Actually increases both of these. So this is kind of Le Chatelier's. So if I increase my Mn2 plus, see what we got. If I increase my iron, I'm sorry, this would be a decrease. 1 molar to 0.25 would be a decrease in concentration. So my Mn2 plus, let's see, that's my product. So if I decrease it, then the reaction is going to shift this way. So my E value would increase. I'm decreasing the concentration of a product, so that means I need to drive the reaction more to the product side to increase that again. Now, my other one, I'm going to increase my Fe concentration to 2 molar, so that happens to be my reactant. So if I increase it once again, I'm going to drive the reaction toward the product because now I'm increasing the concentration of my reactant, and that E value would also increase. All righty, then what we got? All right. So then we have all of this that was really just all a bunch of bonus. All right, so we got a couple of reduction reactions going here. We don't know what X is yet. A strip of tin and a strip of unknown metal are used as electrodes. When the switch is closed, the tin electrode increases in value. So that means this tin has to be the cathode. So here's my cathode. Here is my anode. So the electrons, I think eventually you have to put arrows here. My electrons are going to be traveling this way. So when they travel to this, to this cathode, when they travel to that, then that's going to be a negative charge. It's going to cause ions that are on solution to then join that and plate that. That's why you have an increase in the mass. So in the diagram, label the electrode that is the cathode. So kind of something what I just said right there. The increase in mass indicates that the reduction occurs at that tin electrode. And that is why you see an increase in mass of it. B, drawing the arrows, I already did that. For the electrons, C, if the standard cell potential is 0.6 volts, what is the standard reduction of my other one? So this is going to be my total. So that would be 0.60 volts is going to be equal to the one I know. And that is the reduction one. So I don't need to change that sign. So negative 0.14 volts plus X, which is what I'm trying to figure out. So when I bring that over and solve for that, I end up with X is equal to 0.74 volts. So that would be the potential there for my anode. by the time I solve for that X. And then to find the metal, you had to have gotten that value right and then compare it on your chart. And then you would have to have found, I believe it was it chromium? Yeah, it ended up being chromium. So we had a value of 0.74. And you also had to realize that this was the half reaction that got flipped because it was the oxidation half reaction. So you weren't just looking for a positive 74, you would have been looking for negative 74 on here, because it ends up being flipped. All right, and then write an overall balanced equation. See, we go back to this. We had, this one is the one that ended up being flipped. So this was actually X solid gives me X3 plus 3 electrons. So I have a 3 electrons and 2 electrons. So I'm going to have to multiply everything. This one would be multiplied by 3. So I would have a total of 6 electrons, and this one would be multiplied by 2. So my electrons could cancel out. And then you would gather everything else up, and you would have 3 SN2 plus AQ plus 2 chromium. That's going to be your solid. It's going to give me 3 SN solid plus 2 chromium 3 plus. All right, so then they're telling me what would change the concentration to, and now I'm going to use Nernst equation, and it says not to do any calculations. So my Nernst equation is going to be the E of my cell, so it's no longer at standard conditions, minus, I'm sorry, not this, equals to E naught of my cell, which is what I calculated to be 0.60 volts, minus 0.0592 divided by how many electrons are involved. And we had to get it to 6 electrons, so that becomes 6E. And then that's log of my product concentration, which would be my chromium ion, which went to 0.1, and it had a coefficient of 2. That's why it's so important that you get that balance correctly. And then here, my reactant I had to worry about was my 10, and it got changed to 0.50, and it had a coefficient of 3. Remember, solids and liquids are not included in that, so that's why I didn't have to worry about my solids. And then on the basis of your response, would the cell potential E cell be greater than or less than the original one? So a couple of different ways you could have done this. Like I would have given you credit for talking about Le Chatelier's law. On that one, the E cell would be greater or more positive. And once again, because you're changing the concentration and how that affects Le Chatelier's law, the actual official answer was much different than what I was talking about with Le Chatelier's law. It's more of a mathematical process. So they just went ahead and took the Nernst equation and finished that out. So they says that this Q ratio is a number less than 1. When I take the log of it, it'll be negative, and this is already negative 2. So negative times negative is going to give me a positive. So that means my E cell would increase. So I gave credit for probably quite a few things, but this would probably be your best one to prove it this way mathematically if you're actually taking the AP test on it. All righty, I think that finishes that up, and we will have our test tomorrow. Remember, it's over thermodynamics and electrochemistry.